Okay, welcome everyone to the next edition of our Young Mill seminar. I'm very happy to have Devesh speaking to us today about harmonic maps in higher dimensions. Take it away.
Hi, yeah. So I'll be talking about harmonic maps in higher dimensions today. This is mainly the result which will be discussed is 1982 paper of Shane Uhlenbeck, regularity theory of harmonic maps. Okay, here we go. Let's recap some definitions. So let F be a smooth harmonic map between two Riemannian manifolds, M, G to N, H. We can associate an energy to this map, which is half the pointwise energy E of F. And this linear map DF can be considered a linear map between two inner product spaces, and hence has a norm. And we just integrate it over M. Assume M is compact for now for integration to make sense. Yeah, and locally written in coordinates are norm of the DF looks like this. You can check it has the good proper by Einstein convention. Everything contracts nicely, and we get a norm between two product spaces. Okay, so it's difficult to do regularity theory directly when N is an abstract Riemannian manifold, and it's easy to consider variations when we have some kind of embedding. And by Nash embedding theorem, we know that N can be isometrically embedded in some Euclidean space for dimension large enough, which we'll assume for now. So N, H lives inside Rk, delta. Delta is the standard Euclidean metric. We can consider the Sobolev space W1, 2 from M to Rk. This is just L2 maps with first derivatives in L2 as well. And we can define a subset of this Sobolev space, which will be denoted by W1, 2, M, N. So these are Sobolev spaces from M to Rk, which lands inside N for almost everywhere. Seems like a suitable definition. We are allowed to do, we can inherit some properties of Wm, 1 M, Rk, which we know well, and it's considered as a subset of this. It inherits strong and weak topology from W1, 2, M to Rk. It's interesting, but it will be an interesting question to ask. What about the compactness results in W1 to M, N? It has sequential compactness, but it's hard to prove. Okay. The first property which we can derive easily is that the energy functional is lower semi-continuous with respect to weak convergence in W1, 2, M, Rk. This follows from Relic-Kondrachov compactness theorem, or some compactness theorems in Sobolev's theory. It's not too difficult. We have compactness results in M, Rk. Also, one can prove that that this is weakly closed, W1, 2, M, N. And we know that smooth maps are dense in the Sobolev spaces, W1, 2. But smooth maps from M to N may not be dense in the subset of Sobolev space we just defined. Smooth maps from M to N may not be able to approximate these weak weakly differentiable maps well when you're landing inside N. And this was an example given in some of the papers that when you take the radial projection map from B3 to S2, X, which just sends X to its radial projection living in Sn S2. This is weakly differentiable with a derivative living in L2 space. It has a singularity at 0. It can't be defined at 0. And it can't be approximated by smooth maps as well. There's some degree of map argument, which is that you'll have an obstruction when you smooth maps have a degree which this map does not, and which creates an obstruction to approximating this in W1, 2. Sorry. Okay, moving on. Once we have embedded our N inside a Euclidean space, it's rather easy to find the Euler-Lagrange equation of the functional we just described, the energy functional. So with isometric embedding of N, the Euler-Lagrange equation is this, which essentially says that Laplacian of F has no tangential component in N. You can calculate its normal component, which will turn out to be this, or the negative of this. Okay, and here A denotes the second fundamental form of the submanifold we have considered. N inside RL, it's a bilinear form which takes two tangent vectors at N and produces a vector in the normal bundle of N. And we'll call the solutions of one harmonic maps. So these are critical points of the functional. There is some theory how different definitions of stationary point are different here, that stationary point may not be the same as minimizers, and you may not have this equality, but just assume the solutions of this equation will be called harmonic maps for us. Okay, now one more thing which will be a stronger condition in this sense, which is that a map from M to N in sublevels space is minimizing harmonic map if for any V in W1, 2 inside a subset of M going to N which shares boundary with U, the energy of U is less than the energy of V. So if U and V share the boundary values, the energy of U will be less than or equal to the energy of V. And the definition makes sense. It's called minimizing harmonic map because it minimizes energy. Okay, moving on. The celebrated regularity theorem of harmonic maps. So the theorem by Shane Uhlenbeck is this: for n greater than equal to 3, if we have a weakly differentiable minimizing harmonic map, then the singularity set is a closed set. It's discrete for n equals to 3 and has a Hausdorff dimension at most n minus 3 for n bigger than 4. Further, the function is actually smooth outside your closed singular set. I haven't defined what a singular set is. It's the set of points where U fails to be continuous. And yeah, so it says that outside that set, we actually get smoothness, and this it's a closed set. So doing this for general Riemannian manifold, for M, a compact Riemannian manifold, Shane Uhlenbeck considered additional lower order energy terms. So our energy was just this, but they had to consider extra factors coming from the curvature of M. The technique is essential technique is to do this regularity theory on small balls where the metric is pretty close to the Euclidean one. First, you prove it for Euclidean one, and then using this perturbed energy, you can transfer your results from the Euclidean metric to the general metric for M. For our purposes, we will not consider this energy functional with extra terms. We'll just concentrate on the Euclidean submanifold. So M will be assumed to be an open set of Rn, where the integral can be defined. And we'll consider energy without these additional terms, not to complicate our lives. But it can be done. What they essentially do is scale down your M to regular balls, regular size balls, and they control these gamma terms, and all the results they derive actually carry for this perturb integral for small gammas, and yeah, for these small term, if these terms are small enough. Okay. Now we come to another important notion of harmonic maps, which will be energy density. And there is a monotonicity formula associated to energy, which states the following. For lemma, for n bigger than 3, if you have a minimizing harmonic map from Euclidean space, Euclidean open subset gamma to n, then for any point where you can define these balls, so you have a ball of radius r, you have a smaller ball of radius small r. The balls are inside, the distance is chosen such that these balls are still inside the open set we considered. Then if you multiply energy at this ball with capital R to the power 2 minus n and subtract it with the smaller with the same function considered for smaller radius, then you get a positive term on the right hand side. So this quantity is monotone. It's increasing in radius. This essentially this comes from a property of minimizing, that U minimizes energy, and you can play around this function to get this equality. So this establishes, so we can consider the limit of this, which will be denoted by capital theta. So capital theta U at x is the limit where r tends to 0, r raised to 2 minus n, the energy at this ball. By the lemma, by the monotonicity formula, this limit exists since your function is so if you draw theta against r, it will look something like this. We can consider its limit at r equals to 0. the limit exists, and this function will be crucial in describing singular points. It can also be proven that it is upper semi-continuous, and this rightly is called the energy density of U. It describes the concentration of energy at the point. Okay. An important lemma for proving the theorem is this decay lemma by Maury. So if we have a a Sobolev function of first differentiable, W1 to BR, where BR denotes the ball of radius 0 at origin, and alpha is a number between 0 1. If this quantity has some decay, that it's bounded by C, some constant time R raised to 2 alpha, then we gain Holder continuity at a smaller radius. But doesn't matter. We gain Holder continuity at the origin. And essentially what it says is that this additional decay on the right-hand side, you have this quantity controlled by R raised to 2 alpha. This 2 alpha, we can see it in the proof that this 2 alpha implies some kind of regularity, which is Holder continuity in our case. And from what I found, these kind of lemmas are kind of important in these minimizing inequalities. And regularity theorems follows from these kind of decay estimates. And the proof is by Poincare inequality along with Campanato lemma. This Campanato lemma is another form of this inequality where you don't have df, and you replace df with so it's something like this. If this is bounded, and you consider it's I think it should be soup. If you have decay of this quantity, where f this is like mean oscillation of f, and you have a decay on it, this should be a rho as well. Sorry. So it's better. Yeah, it's better to write it this way. If you have a decay of this kind of quantity, then f is Holder continuous. So this, along with Poincare inequality, gives you some regularity if you have some decay estimates. And we see like this is same as proving a decay estimate on the energy density. Okay. Brad did something similar, the small energy estimate in last talk for harmonic maps in dimension 2, but we have this for higher dimensions as well. So this is the main theorem. This is the regularity theorem of the paper, which says that for n bigger than 3, we can find an epsilon small enough and there should not be we can find an epsilon small enough such that if we have a minimizing harmonic map with small energy, then you have Holder continuity perhaps in a smaller ball, but you do gain regularity at a smaller subset if you have small enough energy. If I'm going too fast or if you have any questions, let me know. And this Holder continuity will be proved by the decay estimates we observed earlier, the decay lemma. So we'll prove the following. If our energy is small, we'll find an epsilon small enough so that if our energy is smaller than that, we'll be able to find the theta, which is between 0 and half, such that this energy density quantity at theta naught is less than the energy quantity at a ball of radius 1 multiplied by a small number, where it just needs to be less than 1. So if you have this discrete version of Mori lemma, you have the continuous version as well. So graphically, if I had to plot, so this is my R and this is my theta. So I have some energy at 1, and if at theta I can compare these two values, and there's a multiplicative factor lambda involved which is less than 1, then it will be enough to show that this implies the Mori decay lemma and will have Holder continuity. So we can prove this as follows. So assume that for simplicity theta naught is half, even though in our proof we'll get something much smaller. We can do this for theta not equals to half, and the inequality once proved will work for other center points as well. Okay, so for the crux of this inequality is that if you go to half the radius, you gain a multiplicative factor. And if you do this, so for any r less than half, and for any ball in radius half, if for any x in radius half, if I calculate this energy function, with multiplied by radius to the power 2 minus n, it's less than lambda times this energy function at r, and I can do it iteratively k times to gain lambda raised to k. So I'm at a much smaller ball, but this and I can compare it with lambda to the power k, the energy function at ball of radius r for all r small enough. Now for any r, I let k be the number such that r is between 1 by 2 raised to k and is smaller than or equal to 1 by 2 raised to k, but bigger than 1 by 2 raised to k plus 1. Essentially, that k is greatest integer function of this log r base 2. Then the energy function, the energy density at radius r will be lambda k multiplied by this lambda k multiplied by the energy density at 2 raised to k times the radius we consider. We gain a factor of lambda raised to k, and this is still less than the energy of u at ball of 1. 2 raised to k r is less than 1. So, and by monotonicity, that you have this inequality, monotonicity of energy density. Okay. Doing this k times, yeah, like we have gained lambda raised to k factor, and k will be less than negative log 2 base r. Now we use this high school identity that if we have a number and it raised to log something base 2, we can replace r and lambda. So this is equal to r raised to minus log lambda base 2. And we're almost there. We have a constant, and which will denote by alpha. So alpha will be negative log lambda base 2 over 2. And this is the decay estimate we want. So our energy density is decaying by r raised to some positive power. It doesn't matter what the power is, it just needs to be positive. And this decay is enough to imply Holder continuity by Maury's lemma. So, okay, this discrete version implies continuous. And so we'll focus on proving this discrete one, that we just want some small enough theta such that we gain a multiplicative factor when comparing our energy to the ball of radius 1. Any questions? If you have any questions, let me know. And this is where the crux of estimates will come. It requires some hard work to gain this multiplicative factor. Okay, so let's assume for now that the energy of U at ball of radius 1 is epsilon square. We have a radial mollifying function psi, which is supported inside ball of radius 1 and has volume 1 and has integral 1. Don't be scared by these constants. We just want an averaging mollifying function with around small enough radius. So let h bar be epsilon raised to half, tau be epsilon raised to 1/4. It doesn't matter what h bar and tau are. These are just small enough numbers based on epsilon, and we do not want them to depend on other quantities. And let theta be between tau and 1/4. And let h be a radial function satisfying the following. So at before theta, it's h bar. After theta plus tau, it's 0. And we have some control over its derivative between these. And like its derivative is controlled by some power of epsilon. And we'll define a convolution of U, some kind of smoothing, with this quantity. So U of Z is multiplied by this mollifying function, and you can consider this as a weighted average of U, but we have weights depending on mod X. So psi is a mollifying function. It smoothens out, but not necessarily smoothens out, but it is like an averaging function when done in this integration. The point of doing this complicated calculus is that we want this averaging to depend on x. The smaller, the closer x to origin is, the better averaging we want out of this function. And the reason for doing this is u is restricted to lie inside n almost everywhere. But we want to do calculus assuming that u is inside Rk with close enough approximations, which will be these u superscript h, these averaged, weighted average of u. So these u's live inside Rk for now. We have let go of the condition that these functions are inside the manifold n. Okay, so we have for small enough for x in ball of radius half, this weighted average will be close to n, since this can be made as close to u we like by choosing appropriate constant of this mollifying function, and it can be done by, so distance square of this function from the manifold n is less than the average of its distance from u of y, where y is varying over ball of radius 1, and this is a weighted average of u of y. We can consider some weighted generalization of Poincare inequality to get this inequality. I'm hoping this Poincare inequality will be true as well, but I haven't checked. So up to a constant, we do get that the distance square is less than the energy of u at ball of radius 1, which is some power of epsilon. Again, can be made as small as possible. Yeah, one more assumption. Assume n is compact now. Okay, for epsilon small enough, we can make this weighted average function of u as close to n we like. And in particular, we can consider, because of compactness of n, we can consider its delta neighborhood, which will be smooth as well for small enough delta. And the energy of this weighted average of u is also close to the energy of u if up to a constant. These constants will just depend on the mollifying function we consider, but we can bound those quantities. So this is also as small as we would like. And if its energy is small, by Poincare inequality, we can bound the diameter of its image as well for ball of radius half. So we have this ball of radius 1 inside it ball of radius half, where we are defining our function. This is going inside n, which is isometrically embedded inside a Euclidean space. So we have two functions, the u, some point in x, u lands inside here. This is u of x, and we are considering some average. So h of x does not land, is close to u of x, and we want to do calculus because we are inside Euclidean space, and we want these approximations to be good to get the energy estimates we want. We'll essentially do the estimates on this weighted averages and then approach how close U superscript H is to U. And yeah. Okay, since we can consider delta small enough such that we have a smooth nearest point projection map, which is, so we have a n embedded inside Euclidean space, and for delta small enough, we can, the map which just projects points in that delta neighborhood to the nearest point of n. So this will be called pi delta. Is smooth. We can choose a delta small enough. Okay. Also, by energy minimizing we can also control the energy on this annuli. This will be important later on, but we can skip this for now. The energy of oh, I missed this. Sorry. Okay. So we have this weighted averages U superscript H landing in Rk, but quite close to the function U. We can do calculus on UHS. We can add, subtract, since they are inside a vector space. We can do convolutions. But to do one more step of approximation, we just compose this with nearest point projection map. So this will be denoted by U subscript H. U subscript H is just nearest point projection of these weighted averages of U. And this lands inside N. These have codomain inside N. And using some string of inequalities, we'll say that we'll do calculus around U superscript H and then project it, and these functions will be close enough. The calculus we want to do, the approximations we want to do will work on UH. We'll bring these maps down by U subscript H, which again will be close enough to the U we wanted. And a part of this is this inequality that after your nearest point projection, you can control its energy in some annuli, and this energy will be comparable to some other annuli of U. I can skip this for now.
So I think this is where smallness of the energy is used. Is that right?
Here?
In the green picture, if you like. If the energy is large and the image of the U in R to the K is sort of goes past where pi is smooth. I mean,
Yes. We want, we haven't chosen our epsilon yet.
Yeah.
And we want epsilon to be small enough such that we are inside a delta neighborhood which has smooth nearest point projection.
Yeah, I mean, if you have a harmonic map which wraps around some hole in N, then you may not be able to find the small enough neighborhood. Its energy be too large, you won't be able to find a small enough neighborhood.
Yes.
By
Yes.
delta naught, I think. Is that how it works?
Yes, it's part of the proof.
Thanks.
Yeah. One more string of comparison theorems we'll need to do. So let V be the solution of Dirichlet problem with this boundary value. We don't, I may have notation from two sources. So if you see H bar, assume it's H. Okay, so now we have a close approximated function which lands inside N, and we want to solve this Dirichlet problem on ball of radius half. So UH, again by some string of approximation, is not too far from U superscript H, and in fact is epsilon raised to half close. And since we are solving Dirichlet problem, the harmonic map V will also be inside this ball by open mapping theorem or maximum principal theorem of harmonic maps. Wherever your boundary is landing, the harmonic map in the interior will won't exceed that boundary. And this will be a good comparison function later on. So at ball of radius half, V does not differ far too much from UH. It's this distance is less than the oscillation of the boundary value, which can be controlled. Now, for a harmonic map, its norm square is subharmonic, so it satisfies mean value property. Essentially, that if I take ball of radius 1/4, its supremum will be less than its integral inside ball of radius half. By minimizing property of, okay, I may have written this twice. Now V is solution of harmonic map. So it minimizes in RK. We are inside RK now. We are not inside N. This minimizes Dirichlet energy. So the Dirichlet energy of this function will be less than the Dirichlet energy of UH, which again is small enough. So it means that we have this extra factor coming in. So if I integrate energy of V on ball of radius theta, I have a theta raised to N coming in because its supremum is bounded. By triangle inequality, we can consider the energy density at theta, and we can split it between two parts. So this difference between U, H, and V, both of these can be compared. I'm going to skip this part. Ultimately, you end up getting this. So its energy with its energy density at ball of radius theta is you gain this factors. You gain 1 theta square and 1 theta raised to 2 minus n with some epsilon powers. We are not quite there. This is not the function we wanted on the left-hand side, but this can be made as small as we would like by making theta small enough. So the last part of the theorem is comparing this left-hand side and replacing it with UH. This was our weighted approximated after point projection of U. Okay, let alpha n be a number small enough, which will be chosen later, and theta bar be a power of epsilon. which epsilon to the power alpha n. Alpha n will be a dimensional constant only depending on n. And this we consider this interval between theta bar and 2 theta bar and divide it into subintervals of length 3 tau. So it will have at least p many subdivisions between theta and 2 theta bar. And so this is union of this i's where these subintervals have length 3 tau. And if we calculate the energy between these two radii, we'll get a sum. And from the sum, we'll have some interval where the energy is less than the average. So there will exist a j, so that the energy at ij of this annuli, ij is sub interval of length 3 tau, where its energy is less than energy of u at ball b1, the whole ball, divided by p. P is the count of subintervals between this. From this subinterval, let theta be the number such that this subinterval starts from theta minus tau and ends at theta plus 2 tau. This is why theta we earlier defined had to be a variable. And this theta is involved in the averaging function h. So we had some theta small enough variable theta plus tau, and we were defining our average, the mollifying function dependent on h, where h in turn depends on this theta. It's only far end of the proof I get to know why theta is a variable. Okay, now we start with the energy density at theta bar. It's comparable to theta, like by monotonicity. Theta bar is less than theta. And we can go some extra length as well, still adding positive quantities. The point of doing this is that at theta plus tau, our averaging function is just one. It brings back u h. So sorry, theta raised to 2 minus n at this larger radius is less than energy density at u subscript h of x. This is because u was chosen to be minimizing, and h, these two functions match on the boundary of this b theta plus tau. So u equals to u subscript h on, and this is because h of theta plus tau vanishes on theta plus tau, and your averaging function is equal to the function you started with on this boundary, after this boundary as well. So the the approximations done before were for this u subscript h, nearest point projection of your another set of approximating functions. And we were able to obtain a bound on this with a constant as small as we would like. Further, UH can be well approximated. There's some string of inequalities, not too difficult to do. which says that we have the approximations we wanted. We ultimately gain a factor, which is like this: C multiplied by some epsilon raised to some powers. And by choosing those powers well enough, we can make this less than half, less than one, in fact, which implies discrete Maury's lemma, which implies decays, which implies Holder continuity. How much time do I have?
About 5 minutes. Is that okay?
Okay.
Yep.
Okay. Yeah.
Awesome.
This ends the small energy proof, that if you have a energy small enough, you gain Holder continuity on a smaller ball. And this proves that this implies a nice characterization of energy density function. So for n bigger than or equal to 3, for a minimizing harmonic map, the energy density at singular point has a energy gap. It can't be smaller than epsilon square, because otherwise it will be Holder continuous. Holder continuity with some elliptic regularity will imply smoothness, and smoothness will imply that your energy density is actually 0, which is the content of this corollary. So for n bigger than 3, if I have a minimizing harmonic map, the singular set is given by this. You have a gap in your energy density, epsilon naught square. And in fact, this is, and when you don't, and continuous point will have this equal to 0. Furthermore, you can prove that the Hausdorff dimension of singular set is less than or equal to n minus 2. Yeah. And this is not too difficult to see after I'm black boxing elliptic regularity, but once we have that, it's fairly easy. So because of the small energy estimates. So if we have a non-singular point, then U is continuous around x naught. U is and by higher regularity theory, we can conclude that U is smooth. Might be a little circular with the definition of singularity. I'll have to check, but this part is easy. So if you have this equality is easy to see, that if you have energy density smaller than epsilon naught square, you gain Holder continuity, which implies smoothness. And when you go back to calculating your energy density, so you have limit r tending to 0, r is to 2 minus n, integral of energy, and this is smooth now. So I can bring down r to the n and consider this weighted integral of energy, which will be some constant or bounded, doesn't matter, multiplied by a factor of r square. As r tends to 0, this goes to 0. So at non-singular points, you have energy density equal to 0. And at singular points, you have a gap. From this characterization of singular sets, it's not too difficult to show that your Hausdorff dimension has to be less than or equal to n minus 2. The Schoen-Uhlenbeck theorem is little stronger. So they improve one more dimension. They say that its Hausdorff dimension is at most n minus 3. But the results we have so far allow us to conclude that result for n minus 2. And there's one more step. There's one more part of the paper where they bring this Hausdorff dimension down by 1. Okay, I'll conclude here.
Sorry, Devesh, I didn't hear that last bit.
So this is not the last result of the paper. They actually prove that n minus 3 its Hausdorff dimension is less than n or equal to n minus 3. So far, I've only done n minus 2.
Cool. All right. Thanks for that.
Yeah, this
Much
factor,
appreciated.
this 2 minus n factor and the energy gap allow us to do this n minus 2 result, but n minus 3 requires some further techniques.
Okay. I guess I'll ask if there are any questions or comments from people. Peter.
You have that the Hausdorff n minus 2 measure is 0 as well.
Yes.
Right? So
yes.
It's a bit stronger than the singularity set is at most n minus 2. Yeah.
Right.
Yes.
True.
Yes.
So if anyone interested in the history in Australia, I don't know whether people want to hear this.
Yeah, definitely. Go ahead. Absolutely.
When Leon Simon came to Canberra in 81, he started up an analytic techniques in geometry study group, weekly study group. And in early 82, we got hold of, Leon was Rick Shane's PhD supervisor in New Nuremberg. So I suspect they posted a preprint to him because we had mail in those days, not email. And we worked through Shane Nuremberg paper in early 82. I can't remember who led that. I don't think it was Leon, and it wasn't me. It might have been Klaus Ecker, who might have just arrived as a postdoc. I'm not sure. It was the year before Gerhard Huesken arrived. When we got to the monotonicity formula, Leon said that he wondered why they only did it for minimizing harmonic maps rather than for stationary. He said in minimal surface case, you could do it for stationary. So I asked him how he did it for stationary, and he said what the technique was in minimal surfaces. So I did that for harmonic maps. And also around that time, in the previous few months, I'd been convinced that, in telling people like Leon that there was a very close parallels between harmonic maps and other geometric variational problems such as Yang-Mills, and whatever you could do for one, you should be able to do for the other, or something analogous. And so a bit later, I did the monotonicity formula for Yang-Mills and for stationary Yang-Mills and harmonic maps. And then I spent quite a long time trying to prove the analogous regularity result for Yang-Mills, i.e. n-5 instead of n-3 regularity for Yang-Mills. But there was the monotonicity. Yes, the ingredients were going to be the same. I thought monotonicity formula, which I could do, epsilon regularity, which I couldn't do, and then dimension reduction from n-4 to n-5, which I suspected was going to be straightforward. There's some complexities about these things. That n-5 result's been announced, but not appeared by Petrarch and Riviere a few years ago. Intermediate results by Terry Tao and Gang Tian. There's a subtlety which I don't understand. I haven't worked in this area since 83 or so I don't understand it anymore and don't understand my own paper. But there's a subtlety between that Tian mentioned in his 2002 paper. It's the difference between the blow-up set and the singularity set. I mean, I almost wrote down the conjecture, the n-5 conjecture in my paper, and I really tossed up about doing that. I thought I made it pretty clear to anyone who worked in the area that I was conjecturing that there was an analogous result to harmonic, the Shea-Nuremberg result. And I said, one might ask whether the positive density set is the singular set in a suitable sense. We're a long way from answering such a question. So that's basically the harmonic map result that Devesh just wrote down last, which was the positive density set is this scale density. The positive density set is the singular set. And that's the essence of the epsilon regularity result, which it was a different Murray. I was going through Murray trying to find a suitable Murray lemma. There was while there might be an analogy, and that's what I thought there was, nevertheless, the way it works out is different. So, you're not looking for a Murray lemma that guarantees continuity. You're looking for a Murray lemma that I think guarantees boundedness or something. It was a different type of result. Anyway, so I played around with this for a while and around those times back in 82. And then I think my good friend Leon, I think, thought I should work harder and keep working to try and get the regularity result. But I didn't have the perseverance. And when Rick Shane visited in late 82, I think I asked him whether he thought I should just publish. I told him I couldn't do the epsilon regularity and asked if he thought I should publish some monotonicity, and he said, yes, of course. So, if it wasn't for Rick encouraging me, I probably would never have published that monotonicity result. Anyway,
good you did. Good you did, in my opinion. Good that you did. Yeah.
Yeah, so that's some history.
Oh, it's really interesting. Thank you for that. Any other questions or comments before I stop the recording? All right. Thanks, Devesh.
Thank you.